Simple frame analysis. We'll jump into the topic of frames now. Okay, that's the question. For the following frame, draw the normal force diagram, shear force diagram, and bending moment diagram. Okay, let's get started. Sign convention. In general, for the forces, whenever the horizontal force is pointing to the right, it's going to be positive. Whenever it's pointing upwards, it's going to be positive. And for the moments, whenever it's counterclockwise, we'll consider it by default as positive. Now, what about the internal forces for beams? Okay, that's the left hinge or the left support of the beam, and if we make a cut, we will see a normal force, a shear force, and a moment. If we take a section of the beam and look at it this way, but the same section, but looking at the other end, the normal force is going to point the other way, the shear force is going to point upwards, and the moment is going to be clockwise. This is the way we look at the internal forces. If you are looking at the section at the left, it's going to be the shear downwards, the normal to the right, and the moment is counterclockwise. And if you are looking on to the left section, is going to be the shear upwards, the moment clockwise, and the normal to the left. Now, how can we see the internal forces for frames? Here's a frame A, B, C, D. Now, I'll try to imagine if I'm holding the frame, member AB with my left hand and member CD with my right hand, and trying to stretch it apart as shown. So an intermediate step is going to be the one shown right now, but eventually if I keep stretching, I'm going to end up having a beam, a horizontal beam. So I can use the same convention or the same way we looked at the internal forces for the beam in the previous slide. Now let's look at it in a frame without this stretching. So this is a general frame. I'm gonna remove the parts in the middle of each member so we can look at the internal forces. We'll start with this one. So this is how we look at it, and if you think about it, if you tilt your head to the left while looking at this, it's exactly the same way we drew it for the beam. The second one, again, tilt your head to the left and look at it, it's exactly the same way we drew it for the beam. Okay, for this one, just forget about the previous two. Look at the one I'm showing right now, which is this one. It's exactly the same we drew it for the beam, and this one is the same for the beam. Now for the last one, try to tilt your head to the right. If you do that, you'll find this the same way we drew it for the beam, and exactly for the last one it's the same thing. So let's all agree on this way of looking at internal forces so we can go ahead and solve the problem in hand. Okay, again, that's the problem we have. Now let's get started. First step, reactions. Okay, before we do the reactions, remember, all the distributed loads should be concentrated loads. So the load on the member EF has a value of 0.5 kilonewtons per meter. When you concentrate it, you multiply the 0.5 by the length, you get 2 kilonewtons. Same thing for the CE member. We have a distributed load of 1 kilonewton per meter. To concentrate this distributed load, you multiply the 1 times the whole length. The length is 2 plus 8, that's 10, so 10 times 1 is 10 kilonewton. And the 10 kilonewton is acting at a distance 3 from the member AD, or just simply at the middle of the member CE, which is 3 plus 2, that's 5. So because the total length of my member is 10. and for the 2 kilonewtons it's acting in the middle of the member EF, which is 4 meters away from point A vertically, and basically it's 2 meters from the point of action to either F or E. Now, what do we have? We need to apply the equation of equilibrium. Summation of the forces in the X equals 0. What do we have? Fx minus 2 equals to 0. That's it. So now we can solve for Fx. So Fx is 2. Now, the summation of the forces in the y direction should be equals to 0. So what do we have? We have Ay plus Fy equals 2 kilonewtons plus 2 kilonewtons plus 10. So 2 plus 2 plus 10 is 14. So the equation is Ay plus Fy equals 14. That's our equations with two unknowns. So we need one more equation. What is the third equation of equilibrium? It's the summation of the moments about a point. So let's, I picked point A. So the summation of the moments about point A should equal to 0. Okay, how do we do this one? It's a long equation, but we can go through it step by step. If I'm rotating or summing the moments about A, I usually like to start with the very far force, like Fy right here. So it's Fy multiplied by 8. And the rotation is positive because it's counterclockwise. That's what I'm assuming right here. Then it's 2. This 2 right here is the Fx. It's rotating about A. It's 2 multiplied by this distance 2. And the rotation is clockwise, so it's negative. That's the negative sign. Then we'll have 2 kilonewtons multiplied by 4. That's the 2, and that's the 4. And it's positive because it's counterclockwise. Then we're gonna have the 10 multiplied by the 3, and it's clockwise, so it's negative. Then we'll have the 2 multiplied by the 1. About A, it's clockwise, so it's negative again. And the last one is 2 multiplied by this distance, which is 2, and it's counterclockwise, so it's positive. And the whole thing should equal to 0. Now I have an equation with one unknown, which is Fy. I can simply solve for Fy to be 3 kilonewtons. Since I have Fy right now, I can go back and substitute into equation 1, and I will get Ay plus 3 equals 14, so simply Ay is 11 kilonewtons. Now I solve for Fx, Fy, and Ay. That's all I need, folks, for solving the whole frame. Now, remember, the ultimate goal is to draw the shear and bending moment diagrams plus the normal force diagram. What I can do now, I go member by member and try to cut the member, take a section or cut through a section, and look at the internal forces at these points by remembering the way we did in the previous slides. This way we can solve for these unknowns. Remember, we have a normal force, we have a shear force, and we have a moment, bending moment. So we have 3 of those, and we have 3 equations, 3 equilibrium equations, so we can solve for these unknowns. I started with member EF, so it's shown right here. I have a VE, which is EX, the shear force in this member. It's the horizontal or X direction force, and we have a normal force, NE, which is EY. and I have an ME, a moment. And please remember, this is the way we drew the internal forces if we cut the member and tilt our head to the right. Okay, just remember that. Now I have these three unknowns. What I can do, I can go ahead and do the equilibrium equations. When I apply these equations, I'll have, in the x direction, I have 2 minus 2, and remember, we need to concentrate these forces. Any distributed forces should be concentrated to do the moments and all the equilibrium equations. So it's 2 to the right, so it's positive, minus 2 plus EX should equal to 0, so EX equals to 0. So if I have a member that's connected to point E and it's a horizontal member, this new member will not have a normal force in it, because the shear force coming from this member equals to 0, or the horizontal force coming through point E equals to 0. Now let's do the Fy. Summation of the Fy, forces in the y direction, equals to 0. So I have a 3 plus EY equals to 0. So EY is minus 3. So the way I drew it, I assumed it to be this way. So it should point downwards. And if you have a member and the two forces are pushing the member, basically the member is in compression. Just keep this note in mind. Now I'll do the summation of the moments about point E. Should equals to 0. Okay, what do I have? Negative ME, because it's clockwise, minus 2 by 2. This 2 multiplied by half the distance, half the force 2. Okay, and the rotation is clockwise, so it's negative, plus 2 multiplied by 4, that's the 2, multiplied by the whole distance 4. So if I solve for ME, it's going to be 4 kilonewtons meters. Okay, let's jump to member DE. Member DE, that's the member DE. I'm going to look at joint E. I'll make a cut at joint E. So what do I see? VE and ME. And remember, there is no NE, because remember the member we just analyzed before had no shear force. So the shear force at the other member corresponds to the normal force in member DE. Since it was 0, so there is no shear force or no normal force in the member DE. So it's even simpler. Now I need to solve for these two unknowns. Okay, concentrate the loads, and here's the note: no normal force in member DE since EX equals 0 from previous step. Now we know summation of the forces in the y direction should equals to 0. Okay, so let's do that. Minus VE minus 10 minus 2 plus 11 minus 2 should equals to 0. That should equal to 0. So solving for VE will give me minus 3. So the shear at this point here is minus 3. Now the summation of the moments about point E should equals to 0. So ME, now 2 times 10. That's the 2, and the 10 is the distance between C and E. And the rotation is counterclockwise, so it's positive. Now we'll do the 11 times 8, and it's negative because the rotation is clockwise, plus 2 times 7. The rotation is counterclockwise, so it's positive, plus 10 times 5. That's the 10, and that's the 5, and it's positive as well. Now I can solve for ME to be 4 kilonewtons. So the shear here, the shear at point E is negative 3, and the moment, the end moment here is 4 kilonewtons meters. Member DE again, but now I'm gonna look at this end. which is at joint D. I have a VD and MD. I concentrate this load, the distance here is 2, and the value of the load is 1 kilonewtons per meter, so the concentrated load is 2 kilonewtons, and it acts at a distance 1 from D. Again, no normal force in this member. Summation of the forces in the y direction should equal to 0. What do I have? Negative VD minus 2 plus 11, and I have a minus 2 again. So VD is 5 kilonewtons. So the shear here is positive 5. Now if I do the summation of the moments about point D, MD, now I'll go to this force, which is 2 times 2. That's the 2 kilonewtons times 2 meters. That's the distance. And the rotation is counterclockwise, so it's positive. Now, 2 times 1. Again, the rotation is counterclockwise, so it's positive. Then I'll have this 2 times this 1. So it's 2 times 1, and it's negative because it's clockwise. The whole thing should equal to 0. Simply, if I solve for MD, I'll have a negative 4 kilonewtons meters. So the moment here at this end is negative 4 kilonewtons meter. Member CD. I would like to take a look at joint D again. So what do I have? VD, MD. Now I concentrate the load. A quick note, I'm making a cut in the member CD. That's why you see the other members to be dotted lines, so they don't come into play. Okay, again, no normal force in this member. Now I'll do the summation of the forces in the y direction. Negative VD, negative 2 should equal to 0, and I'll have a VD minus 4 kilonewtons. So the shear to the left of joint D should equal to negative 4. Now let's do the summation of the moments about point D. I'll have MD, then I'll have 2 multiplied by 2, and it's going counterclockwise, so it's positive, and 2 multiplied by 1, same thing, counterclockwise, it's positive, should equal to 0, and I can solve for MD to be negative 6 kilonewtons meter. To the left of joint D, just a little bit to the left of joint D, the shear force is negative 4 and the moment is negative 6. Now we're done with this member. Let's do member BD. This is member BD, that's the one. I'm looking at joint D, this joint. So I'm cutting just below joint D or node D. What do I have? I have a normal force now, and I have a moment, but I don't have a horizontal force. Why is that? Because the horizontal force comes usually from this member or this member, and the horizontal force in BD, it's the normal force in CD or DE. But remember, these members CD and DE had no normal forces, so they don't transfer any horizontal forces here. That's why I only have a normal force, dy or nd, and md, the moment. Okay, and that's what I just said right now. Summation of the force in the y equal to 0. So nd minus 2 plus 11 should equal to 0, and nd is negative 9. I'm assuming it to be upward, so nd should be downwards. Then you know that BD is in compression. Now the summation of the moments about point D should equal to 0. MD, of course, this force doesn't come into play because it passes through the point of rotation. So the only one I'm worried about now, or I should care about, is this force, the 2 kilonewton, that's acting on member BB prime. So it's MD, then 2 multiplied by 1, and it's rotating clockwise, so it has a negative sign and should equal to 0, and MD should equal to 2 kilonewtons meter. That means in member BD, just below the joint D, we will have a moment of a positive 2 kilonewtons meters. Now I'll look at the small member BB prime. What do we have? If I make a cut before the joint on the left, I'll have, and I'm looking at the right part of the beam. Now I have a shear force going up, and I have a moment going clockwise. How do I solve for these two unknowns? Two equations. And note, there is no normal force in this member. Two equations, they can solve for two unknowns. First equation is the summation of the forces in the y. Sigma Fy equals to 0. That means VB going up minus 2 should equal to 0. VB equals 2. Now, summation of the moments about B should equal to 0. MB plus 2 times 1 should give me 0, and MB is negative 2 kilonewtons meters. Member AB, joint B. Now it's the last member. It's member AB. What do we have at this member? We have a normal force and we have a moment. But again, think about it. There is no way this moment will have a value. It should be a 0 value. Okay, you say so. So how do you know? Just think, what kind of force do you need to produce this moment? If it's not a concentrated moment, you need a force to produce it. And how do you produce it? If you have a moment or a force and a moment arm, and the force should be perpendicular to the moment arm. Okay, if we are rotating about point B, there is no force perpendicular to point B that doesn't pass through this point. This force passes through the point of rotation. This force passes through this point of rotation, so they don't create any moment. Note, no shear force in member AB, since there was no normal force in B prime. Remember, this is the small segment is B prime, had no normal force in it, so the normal force in this one corresponds to a shear force in this. Since it didn't have any normal force, that means AB will not have a shear force at or close to joint B. Summation of the forces in the y should equal to 0, so I'll have NB plus 11 equals to 0. So NB equals minus 11. The correct NB should be pointing downwards because I have a negative answer here, so the member AB is in compression. Now, summation of the moments about B equals to 0. MB simply equals to 0 because there are no forces that counteract this moment if it existed, and it doesn't. Now member EF. These are the values we got for member EF. We had EX equals to 0, EY equals to minus 3, K minus 3 kilonewtons, and we got now we'll try to draw the shear and bending moment diagrams plus the normal force diagram for the whole frame, but we're gonna take them member by member. This is what we have for member EF. EX equals 0 kilonewton, EY negative 3 kilonewtons, and ME equals 4. This is the member with the values. What we see right here is the normal force diagram, and remember we said it's on compression, and the value is 3 kilonewton. Okay, for this one, it's a shear diagram. So it starts at point F with 2 kilonewtons pushing this way. Then it will decrease gradually, going up until it reaches a 0. Why a 0? Because that's what we got. It's EX right here. And because we have a distributed load that will act to push us to the left 0.5 kilonewtons every meter we go up. So we'll end up having this shape. And for the moment, we start with a 0 and we end up by a 4 kilonewtons per kilonewtons meters. Why 4? Because that's what we got. But what about the shape here? Why is it shaped this way? Since we have a distributed load, the moment diagram will be curved. And since we have a gradually increasing or decreasing shear force diagram, we will have a curved bending moment diagram. And basically that's a relationship between integration and the derivative. If you differentiate the equation for this line, you should get the equation for this line. If you basically if you try to differentiate the equation for the moment, you'll get the equation for the shear. And that's a little bit it will be covered later on in other videos, but this is how you distinguish between, or how to know why do we have a moment diagram that has a straight line and why do we have a moment diagram that has a curved line. Remember this: if the shear force diagram is straight and has the same value all over the beam or the member you are studying, the moment diagram will be increasing or decreasing, it depends, but it will be a straight line, not a curved line. And if the shear diagram has an increasing or decreasing value or line, immediately the moment diagram should be curved. Okay, let's take a look at member ED. So these are the values we got for ED. At E we have a shear of -3, a moment of 4. At D we have a shear of 5 and a moment of -4. And we have no normal forces. So the normal force diagram will be just blank. This is the line for the shear force diagram. So we start with the left. We have 5 kilonewtons going up. Why the 5? This is the value we got right here, VD. Then we're gonna go straight down until we reach a point. And why straight? Because we have a distributed load that pushes us downwards 1 kilonewtons for each meter we move to the right. So what is the value at the end right here? It's 3, -3. That's the value of the shear at point E. And that's what we got. For the moment, we'll start by -4 because that's what we got from our analysis. And we'll end up with a 4 to the other end. But before I continue doing this, take a look at the shear diagram. It crosses the horizontal axis at a point. And whenever the shear diagram crosses the horizontal axis at a point, that means there is a maximum moment at this point. So, and the other point is, remember, is it going to be a straight line for the moment diagram? Is it going to be a straight line or a curved line? It's going to be curved because the shear diagram is gradually decreasing. So it will look something like this, and it will end up, again, we have a maximum point right here below the zero shear, and it will end up at a distance here which is 4, and that's what we got from ME. The question is, what is the value of the maximum? Because remember, at the end of the day, you are asked to find the maximum moment and maximum shear, because that's the design criteria you're gonna be thinking about when you are doing the design. Okay, the oldest trick in the book. How do we do this? If we know the distance x, we can calculate the area under the curve of under the shear curve, and if we do this, we can find the value for the maximum moment. How to find it? This is what we have. Now our task is to find the distance x. I'm gonna change this to this. I didn't do anything. I just moved this line to the left to create two similar triangles. Now, I just said two similar triangles. I will use this trick. So 8 over x is 8, which is the summation of these values but without the negative sign, over 5. These are the similar triangles. Again, it's 8 over x equals 8 over 5. If I solve for this, basically it's x equals 5 meters. Now I can calculate the area under the shear diagram. This area, the area is 12.5 kilonewtons meter. Is that the maximum moment? No, it's not. The maximum moment that happens to be right here, it will equal 12.5 if you start your diagram from the 0 right here, but you started from the -4. So what you need to do is add this -4 to this number to get the maximum moment, which turns out to be 8.5 kilonewtons meters. Now member ED. Member ED, we have this overhanging segment of the frame. We have a VD that's -4 and MD that is -6. So the shear and moment next to point D, we already solved for that. Okay, what about the one at the cantilever tip? The shear is not 0, but the moment is 0. Okay, no normal force. Again, for the shear diagram, I'm gonna go down -2 because I have a concentrated load of 2 kilonewtons. Then, since I have a distributed load that's trying to push me down 1 unit for each meter, so I'm gonna move like this. So I start with a 2, I'm pushed down 1 for each meter, so I'm gonna be pushed 2 units, right? For the first two, it's total of 2 meters, so the first meter I'm gonna be pushed 1, so I'm gonna be at 3. Then for the second meter I'm gonna be pushed another 1, so I'm gonna be at 4, so it's a -4. And without even doing this, if you go ahead and do the -2 and the -4, because you already know the -4 from the VD, and you just connect them through a line. For the moment, at the tip, it's going to be 0. What about at ND? You know that it's -6 kilonewtons meters. So it's 0 here, and it's curved like that, and it's -6. Now let's check the value of MD. Let's try to calculate the area. If we calculated the area of the shape, and if we get the 6, that means our procedure is correct. So we have this area. What is the area of this? It's 2 plus 4 over 2. It's taking the average, then multiplying by this distance, which is 2. So 2 plus 4, taking the average, multiplied by 2 is 6. So we are right. Now, member AD, looking at joint D. This is what we have. This is number, I'm sorry, it should be, that's a typo. It should be member DB. Okay? So what do we have? We have ND, which is 9. And we said before that's BD is in compression. So this is the member, and it's in compression. It doesn't have any shear forces, but it has a moment which equals to 2, and that's how we draw it. It's 2 here all the way up. Okay, let's move on. Member B, B prime. That's the member. Okay, you remember that. At B we have a shear force of 2, and we have a moment of -2, and it's a cantilever segment. So no normal force. For the shear, we'll go up to, move to the right, because we have no forces between B and B prime. Then the 2 kilonewtons is gonna close our diagram. Okay, for the moment, we start with a 0, the tip. It's a straight line, it's not curved anymore. Why? Because the shear diagram is a straight line that's not changing in value. It starts with a 2 and ends with a 2. So if for any reason this shear force was dropping down like this or going up like that, we will have a curved line. But since it's not changing any values, and of course there is a mathematical explanation behind this, but this is not the video for it. Now we have 2 kilonewtons meter, and again this value should be negative. Okay, member AB, which is the, I believe should be the last member we're gonna analyze. We have a normal force NB, which was -11, but we said it should be in the other direction, so AB is gonna be in compression, and we have a moment which is equal to 0. So in compression, and note there is no shear and no moment, because moment is 0, and we said no shear force in member. I believe now we are ready to draw the whole thing or put all the pieces together. For the normal force diagram, what you do, you take the diagrams you drew for each member and just assemble them into the general frame. So this one is the 11 kilonewtons compression, and try to keep the whatever value that is negative, keep it inside the frame, like in the inner part of the frame, and whatever is positive, keep it outside, so you have like a sign convention of yourself. So no forces in member B, B prime, and for B, D we have a 9 kilonewtons compression, no forces in CD, no forces in DE, no normal forces in DE, and we have a compression force of 3 in member FE or EF. For the shear force diagram, that's the frame, no shear in this one, in AB. We have a shear of +2 kilonewtons in B, B prime, no shear in this one, and for this one it's -2 kilonewtons and -6 kilonewtons. For DE, we're just assembling whatever we had before. We had 5 going up and going decreasing like this linearly, and going up here at -3. And for the last part, which is EF, it's gonna be 2 positive in the bottom and negative, or I'm sorry, it's 0 at point E. For the bending moment diagram, 0 moment A, B in member AB. We have a moment in member B, B prime, like that. We have a moment of 2 in member B, D. We have a moment of -6 right here, and we have a moment in DE. We start with a -4, and look at this, the -4 in D, or in member DE starting from point D, if you sum these two numbers, you'll get the negative 4. So it's basically uh, what is the word for it? It's not in it's not the summation. Anyways, you get the idea. If you sum these two, you will get the negative 4 right here. Okay, so and we have this 8.5, and we knew how to do this one, and the 4 right here, and last we have this one, the EF right here. It starts with a 4 on top and curves down to 0. I know it's a long video, it's hard to chew on sometime all in one shot. What I'm asking you to do now is, if you get it from the first time, perfect, that's fine. I know I might go a little bit fast just to keep this video within acceptable limits for you guys, but my advice is the first thing to do is try to draw this again by hand and go through step by step and pause whenever you need, and try to do the math yourself and see if it makes sense or not. Okay, that's all, folks, and I hope you enjoyed or you learned something new, and I'll see you in a future tutorial.